Hello everyone. In this video, we'll discuss briefly about the motion of a body which moves under the influence of the gravitational force. Okay. So here we can divide the discussion into two parts. One case where a body is projected vertically upwards from ground, and another case where a body is dropped from certain height. And next comes many combination of different kinds of cases. First, let's discuss these two basic things. Okay, so if you take a body, the bodies that we normally project, we project with them with such small velocities that the heights to which they go, at such heights, I mean, when they go to such heights, the acceleration due to gravity does not vary much. So we can assume acceleration of the bodies is constant. Okay, and hence the motion of such a body would be uniformly accelerated motion. So we can use the equations that we have derived for the case of uniformly accelerated motion. So all the equations that we have derived, these equations, v is equal to u plus at, v square minus u square is equal to 2as, and s is equal to ut plus half at square. Okay, and we can also use the displacement in nth second and other relations as well. Now let's use these quantities, these relations, in order to discuss a few things related to a body which is dropped from certain height. Okay, so here a body drop from certain height, we will divide it into two special discussions. The first one would be where, let's say, imagine we were on top of a building of height h, body was dropped. So imagine the person was standing there, was holding that particular body. So since the person is standing, since he's holding the body, initially the body will have same velocity as the person. Okay, so once the person releases his hand, basically he doesn't provide any velocity to the body, or he doesn't apply any force. Initially was holding, and when he just releases it, then the body would start to fall under the influence of gravitational force, and as a result it would have an acceleration is equal to g in the downward direction. So here, for the sake of discussion, we will be considering vectors in the downward direction as negative. So I'll take acceleration as minus g. Okay, now two things that I'm very interested to find. The first thing is after what time it would basically reach the ground, and as it is dropped, due to the acceleration, the velocity of the body would keep increasing with time. So now another interest is to find the velocity of the body just before it strikes the ground. First, let's find the time taken by the body to reach the ground. Okay, so in order to find the time taken by the body to reach ground, so what I would be basically using is, I would be using s is equal to ut plus half at square. Okay, time taken. So here s is equal to ut plus half at square, where u represents the initial velocity of the body. Okay, so in this case, since the person just released it, at the moment when it was just released, the initial velocity of the person was 0. Let's assume the time taken by the body to reach the ground is t plus half into acceleration would be minus g into t square. Then what about the displacement? As the body goes from there and it hits the ground, so the magnitude of displacement would be equal to the height of the building, and the direction of the displacement is in the downward direction. So hence I can consider the displacement to be minus h. So minus h is equal to minus g by 2 into t square, or t would come out as root of 2h by g. Just a minute. So we have found the time taken by the body to reach the ground. Next we will try to find the velocity of the body as it reaches the ground. Okay, So basically you're supposed to memorize this relation, okay, and also you must also know the way we got it, because most of the times they may ask problem directly based on relation, but few times the relation directly won't help you. So we may have to have the idea of how to get the relation, or how we can use the equations, basic uniformly accelerated motion equations, to solve a problem. So that's the reason I'm explaining these things. Now let us try to calculate the velocity of the body just before hitting the ground. So to find that, we will make use of the relation v square minus u square is equal to 2as to find v. So v square, v represents velocity of the body just before hitting the ground, minus u square would be 0 square, 2 into acceleration would be minus g, displacement would be minus h. So v square is basically 2gh, or v is equal to root of 2gh. So the v that we got basically here is the magnitude of the velocity, and just before hitting the ground it would have a velocity in the downward direction. So if we take into account the direction also, the velocity can be represented something like this, minus root of 2gh. That will be the velocity of the body just before hitting the ground. Okay, so next the next thing we will try to do, the another case where again dropping itself, but let's say the person who dropped the body, as in this particular case the person was at rest at a height h when he dropped the body. So the next case what we will consider, let's say the person who is dropping the body is initially in some kind of plane or something like a balloon which is raising upwards. So let's consider something like this. Okay, person is in a balloon at height h and going upwards or downwards with speed, let's say u. Okay, so now this is the situation that we have. Imagine this was the ground. So we will split the problem into two parts. The first part where the balloon was basically at that instant, okay, this is the balloon, imagine, was going upwards with the speed u. So at that instant it was at a height h, so when the body was just dropped. Okay, imagine you were the person inside the balloon and holding that particular body or a stone, something. So if you are holding it, so basically since you are in the balloon, okay, so you would start going upwards along with the balloon. So you would have the same velocity as the balloon. And if you are holding some object, the object would have same velocity as you because it's moving along with you. So at that instant, when you just release the stone in this case will not have zero initial velocity, but basically it will have some velocity of u in the upward direction. So we can say initial velocity is equal to plus u, okay, and acceleration is equal to minus g. Now the first thing I am interested to find is the time taken by the body to reach ground. Okay, so in order to find time taken, I will be using the equation s is equal to ut plus half a t square. So the s would be the displacement of the body when it reaches ground. So basically it will go up to certain height. Suppose if we are the observer observing from the ground, so as soon as you drop it, it wouldn't start falling down immediately. So because of the velocity it possessed in the upward direction, initially it will go to certain height where its velocity would become 0, and then it would start falling downwards. Okay, so it goes up and then it comes down. So now if we look, this was the initial point, let's call it A. So finally, okay, it would hit the ground, let's call that point to be B. So the total displacement is from A to B. So that displacement is basically minus h, which is equal to u So initial velocity is u t plus half into minus g into t square. So basically in this equation, the unknown is the t, whereas the other ones are the known quantities. So if you see, the relation is in the degree 2 of t. So basically it's a second degree equation in t. So it's a quadratic equation. So we will use the formula to find the roots of the quadratic equation. First let's rearrange it properly. Gt square by 2, okay, minus ut minus h is equal to 0, or we can write gt square minus 2ut minus 2h is equal to 0. We would basically have divided by 2, that 2 we can send it to the right side. Then, so if you see t, we would get it as minus b plus or minus root of b square minus 4 into a into c divided by 2a. So if you simplify this, you would basically get, okay, u plus or minus root of 4u square plus 8gh, sorry 2u, I forgot. So here t would basically come out as 2u plus or minus, here we can take 4 common, then we would basically get root 4 would be 2, u square plus 2gh divided by 2g. 2 gets cancelled in the numerator and denominator, so we would get u plus or minus root of u square plus 2gh divided by 2g. So now we got the two values for t, but which is the correct answer? Okay. So if you observe properly, the second answer that you got is going to be negative, okay, because definitely root of u square plus 2gh will definitely be greater than u. So this is going to be negative, hence this can't be the answer. So the answer or the time taken by the body to reach the ground would be u plus root of u square plus 2gh divided by g. Okay, so just understand what relation we have used in order to find the time taken, and what we have substitute in the place of acceleration, velocities and displacement, how we solve the equation. Okay, because they can ask a question based on this particular concept. And then the next thing I'm interested to find is, okay, what would be the velocity of the body when it reaches the ground? Okay, so one way of finding that is, okay, we can directly use v is equal to u plus at. Since we have already calculated t, we can make use of that in order to find the velocity just before it hits the ground. So v would be initial velocity plus u, acceleration minus g, and the time taken by the body to reach the ground. Earlier we got this u plus root of 2gh divided by g. So we would get it as root of u square plus 2gh minus indicating that the velocity would be in the downward direction after that much time, that is when it is just before going to hit the ground. Okay. Similarly, we can proceed for the other case also. Here we have proceeded for the case where the balloon was rising upwards with a speed u. Similarly, if the balloon was going down with a speed u at the instant when the body was dropped, we can proceed with a similar way, but instead of initial velocity as plus u, we have to consider it as minus u, and the rest of the calculations are going to be the same. Okay, so in that particular case, in the next case, we would get the time as time would be minus u plus root of u square plus 2gh divided by g, and the velocity, I mean in the second case, velocity just before impacting the ground would be this. Okay, we would basically get the same velocity uh, from the equations. The Since you already know the conservation of mechanical energy, from mechanical energy we can basically explain why the velocity is coming out to be same in both the cases. So we will do that part discussion in the next chapter. Now let's continue with the discussion of the part where the body is projected vertically upwards from the ground. Okay. Body projected vertically upwards. Okay, so imagine this was ground, for example. Let's say we took a body with a and we projected it upwards. When it was just projected, it had a speed u in the vertical upward direction. As we discussed earlier, when you have the velocity and acceleration of the body in opposite directions, the body would generally slow down, that is, its velocity would basically decrease. After a certain amount of time, it would basically become 0. Since you have projected it with a velocity u, it will keep on going upwards. Okay, somewhere its velocity will become equal to 0. Okay, so basically goes until there, and then it would start to fall along the same line in the downward direction. So when it's going up, as you can see, the velocity is in the upward direction, but throughout its motion, the acceleration, which is basically due to the gravitational force, okay, would always be in the downward direction, and magnitude would always be same. So here also the body is in uniformly accelerated motion. Okay, so here basically we are interested to find a few things. We'll find those things first. Okay, so look at this point, the topmost point where the velocity is 0. We can call it as the highest point in its path. So at that highest point, basically the vertical component of velocity is 0. Okay. Now let's try to find the height of that point from the ground. So in order to find the height of that point from the ground, so we will use the fact that their velocity is equal to 0. So we will make use of this relation, v square minus u square is equal to 2as. So final velocity there, as the body goes from point of projection, let's say point A, the highest point is point B. Okay, as it goes from A to B, final position is B, where velocity is 0. Initial position is, at initial position velocity is plus u. 2 into acceleration is nothing but minus g. I am considering the vectors in the upward direction positive and vector quantities in the downward direction as negative. So as it was projected at A, its velocity was upwards, hence I took it as positive. And as it goes from B to the ground, acceleration would be minus g into, what about the displacement of the body when it goes from A to B? So the displacement of the body would basically be plus h. So we can write minus u square is equal to minus 2gh. Minus minus gets cancelled. Okay, so h would basically be equal to u square by 2g. So h represents the maximum height to which the body will go once it's projected with the speed u. Okay, now the next thing we'll try to find the time taken by the body to reach its maximum height. So we will call that as time of ascent. Time of ascent is nothing but time taken to reach the highest point. So here also, to find that time, we will use the fact that the velocity at the highest point is 0. So we will use this relation. So v is equal to u plus at. Final velocity is 0. Initial velocity plus u. Acceleration is minus g. It's called time of flight as ta. So we would get time of time of ascent. So we would basically get time of ascent as u by g. Okay. So we can also prove the time of descent. Descent is nothing but, so once it goes to the maximum point B, then it would start falling downwards. As it goes up, as it's going up, velocity is upwards, acceleration is basically downwards. So once it reaches point B, velocity becomes 0. Though at that moment velocity is 0, still the body has acceleration in the downward direction, or in other words, still there is a force acting on it in the downward direction. As a result, it would be pulled down, so it wouldn't just stay at B. Okay, so because of the acceleration, it will start to acquire a velocity in the downward direction, basically due to acceleration due to gravity or due to gravitational force. So its velocity will keep on increasing, so it would basically fall down again. So time of descent represents time taken by the body to go from that highest point, okay, to that ground, or the time for which it's been traveling downwards. That's what time of descent means. Okay, so we would basically get it as again u by g. Okay, so time of ascent would be equal to time of descent. So the total time of flight would be equal to u by the time taken to go upwards and then the time taken to go downwards. So total time of flight would be 2u by g. Okay, and next thing here, so the velocity of the body, I mean, we have projected with a speed u. Basically what would basically happen is, okay, here if it was projected with a speed u, let's say this is the maximum highest point, so when it goes from this point of projection to the highest point and then on its way back, okay, so to go up to that point and to go from that point to the ground, it would basically take same time. Okay, so provided that there is no air resistance. So most of the problems that you will be coming across, or almost all, we do not consider air resistance. Okay, because air resistance is a very complicated force. Mathematically describing it is very complicated, and solving equations would also be very complicated when air resistance is involved. Okay, physics would become very difficult in that case, so we ignore that. So in the absence of the friction, air resistance, the time taken to go up to the highest point and from highest point to the ground would be same, okay, as we have written the relation earlier. Next, so now what we will try to do, okay, we will try to prove that if it was projected with a speed u upwards, so then just before hitting the ground it would have the same speed u in the downward direction. Okay, so let's try to prove that. So earlier we already proved that the maximum height to which it goes is u square by 2g. Okay, so once it goes to the highest point, so highest point, that point is at a height of h, which is nothing but u square by 2g. So there velocity of the body is 0. So from there it would start falling down. So basically this entire downward motion is similar to that of a body falling freely from a height h, or it is similar to the motion of a body dropped from a height h. So we already discussed, if a body is dropped from a height h, the velocity of the body just before hitting the ground would be root of 2gh, but in the downward direction. So minus root of 2g into h is nothing but u square by 2g. 2g gets cancelled. We'll have minus root of u square, which is equal to minus u. So minus u will be the velocity of this body just before hitting the ground. So we have concluded that if you project it with a velocity u upwards, then while it's coming back, its velocity would be u, I mean it would have same magnitude but in the downward direction. So mathematically we have proved it. So we already know a good explanation why the speed is same. I mean we can explain that using conservation of mechanical energy. Okay, and one more point here, similarly we can also prove that, okay, here if this is certain point in its upward motion. Here if velocity is something like, let's say, v dash, so at the same point when it's going down, it would have the same magnitude of velocity v dash but in the downward direction. So you take any 2 points which are in the same horizontal level, not 2 points, basically the same point. So whenever the body is crossing that particular point during upward motion as well as during downward motion, the magnitude of velocity will be same. Okay, so one small caution here, I have represented the upward motion and downward motion separately, parallelly. Basically the body wouldn't move like that, it goes along a particular vertical line and it falls back along the same line. The reason why I have represented 2 lines is to make you understand easily and visually see 2 parts. That's the reason. Okay, and next what we will try to do, so we will try to calculate. Okay, sometimes they can ask you what is a if a body is projected vertically upwards, what is the distance traveled in the last second of its upward motion or last 2 seconds of its upward motion, something like that. Okay, so let's say we want to calculate what is distance traveled by a vertically projected body in last t seconds of its upward motion. Okay, so imagine this was the ground, for example, this was the ground, let's say. Okay, and then we projected it vertically upwards. So this is the highest point. So in last t seconds, let's say it goes from this point, let's say point of projection is A. So C is the highest point. So in the last t seconds, it goes from B to C. Then what is the distance between those 2 points B and C? So in order to find the distance, I will make use of this relation Vt minus half At square, the relation which is valid for uniformly accelerated motion. So here when it goes from B to C during its upward motion, so there is no change in the direction of its motion, hence we can say that the magnitude of displacement when it goes from B to C would be the distance traveled. So S is equal to V. So when it goes from B to C, the final point would be the point C, where velocity at C would be the final velocity. So it can be considered 0. The time taken is t. It's half into acceleration will be taken as minus g, because the acceleration is g downwards into t square. So S is equal to the distance traveled is half g t square. Okay, so this is the distance traveled in the last t seconds of its upward motion. Okay, now just see here, this is also the distance traveled, this is also the distance traveled in first t seconds of its downward motion. We can prove it in simple terms. Okay, so once it reaches point C, their velocity would be 0, then it would start to fall downwards. So it's like a freely falling body. So here velocity is at highest point 0. So in first t seconds of its downward motion, let's say it goes from this point C to point D. So let's calculate the distance from C to D. So as it goes from C to D, basically the direction of motion is not changing, hence the magnitude of displacement and distance traveled would be same. So let's calculate the magnitude of displacement, that would be equal to the distance traveled. So to calculate the displacement, S is equal to, I will make use of this relation. It implies S is equal to, so at point C would be the initial point where the velocity would basically be 0, into t plus half into acceleration would be minus g, okay, because it's downwards, into t square. So the displacement of the body as it goes from C to D would be minus half g t square. So what does this minus basically represent? So the minus represents, I mean, as you can see in the diagram, when it goes from C to D, the displacement is basically in the downward direction. So and what is the magnitude of that particular displacement? Half g t square. So which is what we got earlier. Okay, so the distance traveled in the what do we say, last t seconds of its upward motion would be equal to distance traveled in the first t seconds of its downward motion. Okay, this is one conclusion which might help in a few problems sometimes. Okay, and then we have something called Galileo law of odd numbers. Let's discuss that part. Galileo law of odd numbers. So this basically we say for freely falling body. So basically if we have a freely falling body, okay, then the distance traveled by it in successive equal time intervals, okay, the ratio would be in the ratio of odd numbers. So what do I mean by it? Let's say we drop the body at point A, so where velocity would be equal to 0, so it would start falling downwards. Okay, so let's consider, so it basically falls downwards. As it falls, let's consider different points where the time taken to travel between those two successive points would be the same. Okay, B to C to D. So now we are interested to find this distances between, I mean the ratio between the distances from A to B, B to C and C to D. So this ratio we want to find, S B to C, S C to D. If you observe properly, okay, so the time taken between two such points is same. Okay. First let us try to calculate the distance traveled by the body as it goes from A to B. So as we have discussed earlier, when a body is freely falling downwards, first t seconds of its motion, the distance traveled is half g t square. Then what about distance from B to C? Distance from B to C would be distance from A to C minus distance from A to B. So distance traveled from A to C. So the body takes a total time of 2t to go from A to C. Hence this would be half into g into 2t whole square minus distance traveled from A to B would be half into g into t square. This is nothing but, I mean if you simplify you would get this. Okay. Now let's calculate the distance traveled, okay, by the body as it goes from C to D. So which would be equal to distance traveled to go from A to D minus distance traveled by the body when it goes from A to C. So this total distance minus this distance gives us the distance traveled to go from C to D. The body takes a total time of 3t to go from A to D. So the distance traveled would be half into g into 3t whole square minus distance traveled to go from A to C would be half into g into 2t whole square. If you simplify this, you will get it as 5 by 2 g t square. So if you look at these three relations 1, 2 and 3, you just observe them. Okay, so I have calculated for 3 successive time intervals having each time interval of t. So if you look at them, if you find the ratio, the first one is half gt square, second is 3 by 2 gt square, so next t seconds the distance traveled is 5 by 2 gt square, the next t seconds again, the fourth interval, you would get 7 by 2 gt square. So if you find the ratios, we would get it as you can see, okay, odd multiples. Here the t could be basically anything, whatever, either 1 second interval or 2 second interval. In successive equal intervals of time, the distance traveled would be equal to, the ratio of distances would be the ratio of odd numbers. Okay, that's enough for this video. In the next video, I will pick a few problems from this chapter overall, and I will try to do the discussion of the problems. Okay, I was a bit busy in the college because of the advanced. I will try to take more classes from Sunday. Tomorrow and after tomorrow I will try to upload a few videos. Okay, Sunday onwards I'll be uploading more videos. So practice a little bit at home if you are free. Okay, better watch the videos or open book and study if you don't have anything to do. Okay, we'll meet again in the next video. Bye bye.